What you should be seeing now is the introductory slide with the title of my dissertation, Basin and Petroleum System Modeling and Global Sensitivity Analyses of Natural Gas Hydrates, as Steve said. Steve is my primary advisor and the dean of the school. And here's my permanent email address. It's just my full name at gmail.com if you want to contact me for questions after the presentation. A quick overview is we will cover what gas hydrates are, and then we'll dive into the 3 dissertation manuscripts that I've written. The first one is a case study in the Gulf of Mexico to inform an upcoming drilling expedition. The second one is a proposal of the mechanism occurring in salt basins for attractive exploration. And the third will be presented as a novel method approach for global understanding of gas hydrates. Here we can actually see some gas hydrates. This is a match setting the gas hydrates on fire, and they look like ice. They're in solid form, and this just keeps burning. This is actually methane trapped in this solid form. Where are they found? Amazingly, these are found along offshore every continent on the planet. They're widely found. There's about 50 sites that have actually been drilled or inferred. Some drilling production tests have occurred in Japan, as well as Gulf of Mexico, where we've required pressure core, UT Austin, and the Department of Energy. And there's a lot of interest as far as potential energy resource from gas hydrates, as well as geohazards and CO2 sequestration or storage. A quick plug here, if you go on YouTube and just type in Stanford BPSM gas hydrates, you'll see Zach, who just defended his dissertation a couple weeks ago in our BPSM group, and me presenting a 2-minute video on the modeling of gas hydrates. Here you can see that it is a gas molecule trapped in a water crystal lattice. And what's interesting is that 1 cubic meter of methane hydrate, it's found at low temperature, high pressure conditions, such as the ocean marine environment, as we saw, as well as permafrost, but here we focus on the marine gas hydrates. When these methane hydrates are brought to standard temperature pressure conditions at the surface, it becomes a little less than a cubic meter of water and about 170 meters of methane gas. To put this in perspective, it is actually a more condensed or saturated form of gas than other shallow gas reservoirs would be, but not quite as much as something like a deeper gas reservoir, somewhere in between. The first dissertation manuscript will be discussing the 3D basin and petroleum system modeling through time of Terrebonne Basin, Gulf of Mexico gas hydrates. I was very fortunate to have several collaborators, including at Stanford, the United States Geological Survey, and Schlumberger. Some quick highlights are that this is a quantitative 3D basin and petroleum system model for dynamic gas hydrate studies to be used for future drilling recommendations. The model predicts present-day gas and gas hydrate volumes, saturations, and distributions of accumulations, as well as gas hydrate recycling through time and the potential source of gas. We will also present original interpretations of the geology using seismic imaging and well logs in this part of the Gulf of Mexico. So where is it found? It is here in the north slope of the Gulf of Mexico. You can see this dashed red line outlining the Terrebonne Basin. So dark blue here is sediment, and then light blue is salt. Now, if you zoom into this diamond here in red, this is where we have 3D seismic available, which we use for our interpretations. We also use 3 wells that have been drilled for data and inputs for the modeling. Here's a brief glance into how these surfaces were acquired. We did a depth conversion, and then we picked, using the 3D seismic, we traced out some key surfaces, including pinch outs, unconformities, thrust faults, and more. There are actually also extensional normal faults near the depicenter, aside from these thrust faults found here further up dip. Here in the light blue dashes are where we see these normal faults with a pretty small amount of offset, but what's interesting is they seem to be associated with this giant gas mound found in this portion of the mini basin. Now, Hillman et al. 2017 first noticed the presence of these giant gas mounds, but it was still debated in the community as far as what causes them. And we believe that these shallow normal faults, which do not penetrate a great depth so that it would be thermogenically sourced gas, we think that it would be biogenically sourced or potentially from the gas hydrate and gas reservoirs, which are shallow, because these faults create focused fluid flow. Here's an overview of the 3D model inputs and geometry. This is grouped surfaces, so we actually have a resolution of about 3 decimeters and 900 years resolution through time. The naming comes from the literature for the upper half of the sediment in this model. So basically, it has been named all the way down to the pink sand found here, and then we went ahead and interpreted the sediment that is deeper than that. And the naming convention we used is below pink, and then associated numbers through depth, and we abbreviated as BP, kind of as an homage to where I'll be working after I graduate. This model has 25 million cells, and we use a total organic carbon weight percent of 1 and HI, hydrogen index, of 100, similar to the Green Canyon model, which is not far from here. It was a 3D model also published on gas hydrates in the Gulf of Mexico. What's important with case study models in particular is calibration, because this kind of differentiates basin models from theoretical to at least grounded in some sort of data. So what we took is about 7,000 porosity points derived from a suite of well-log curves. You can see them here. The black dots are those porosity points, and then the red line, which is hard to see because it actually lines pretty well, is the model output for each layer. We also used pressure points from mud weights. Now, typically we drill overpressured, so it's good that these points are actually a bit above the output, which is in black here. We were fortunate to also find public 2D seismic available. This 2D seismic imaging is pretty broad, so you can see here the Six Peaks Escarpment in the Gulf of Mexico. And here is the Terrebonne Basin that I showed you earlier. You can see the sediment here, and then this is all salt. Our interpretation is that the salt actually floors this mini basin and may not allow thermogenic gas, which would be generated from deeper within the basin, to migrate upwards into the basin. So we actually use biogenic gas in our model. This is because salt is actually extremely impermeable. What we think is happening here is that salt withdrawal occurs, so that is how we model this salt movement. You can see 18 million years ago, it's salt sheet, and then as sediment is dumping from the northwest, this salt withdraws and moves more downslope, and the sediment kind of fills in that space. Here is an erosional map that we interpreted. You can see that the shape is somewhat similar to what we have as the salt structure in the area, the epicenter being here, and then the salt ridge kind of as this lobe here. So we believe that some salt movement around 1 million years ago occurred, which created erosion of about 200 feet up to 1,000 feet, 200 being the average. One other way that we calibrated is the heat flow. So the heat flow was not really known. I mean, generally in the Gulf of Mexico, it's around 45 milliwatts per meter squared. But here we have the salt influencing that heat flow so that it's actually channeling the heat flow away from the epicenter, and the base of the model is the salt. So we have to consider that. To figure out which heat flow is most appropriate, we kind of tested out different versions so that the base of the gas hydrate stability zone aligns with what we see in seismic. Now, base of the gas hydrate stability zone, this means that in this area in red here, gas hydrates can exist because it's low temperature, high pressure conditions. In the blue, hydrates cannot exist because the temperature is too high. And keep in mind that the sediment layers are deepening in this direction. So this is the base here for this specific layer in the model. The dashed black line is where we see the base of the gas hydrate stability zone in the seismic. And we found that it aligned pretty well when we used a heat flow of about 25. Now I'd like to show you these this qualitative figure that I sketched up because these are pretty important concepts going forward in the presentation. We see here on the left sediment burial driven recycling. What this means is in the brown here, we have a gas hydrate saturation. It's about low to moderate saturation. And then we get sediment burial. As sediment burial occurs, this hydrate that was found here now exits the gas hydrate stability zone, which is here in the dashed white and black line. And when it goes beneath the stability zone base, it turns into gas. It dissociates into gas and migrates back up to the base. This results in a higher gas hydrate saturation. Another way that we think this can occur is by salt heat-driven recycling. So we'll start with something similar here, except we have a flat salt sheet. Now, if this salt were to be a diapir with a different bathymetry, what we would see is that here we have a dome at the base of the gas hydrate stability zone, which can combine with the burial of sediment and create focused fluid flow, which actually results in an even higher saturation because the fluid is really focusing at that base. Here we just have two simple 1D extractions. In the red star, we have an extraction of the gas hydrate stability zone thickness above the salt diapir. And then we have an extraction in the depocenter. And you can see that in the depocenter, the gas hydrate stability zone thickness is much greater than where you are above salt. So what would that mean for the gas hydrate saturations? Well, we took a look at 8 million years ago. You can see here a map view of the top of the salt structure and a 3D view of the top of the salt structure. And what we have in black here in both of these images is gas hydrate saturations that are above 6%. This is around the time when gas hydrate saturations begin to form, and we find that they're highly associated with where we have higher elevation or kind of these salt diapirs. And so we found this curious, and we thought that perhaps this is the heat flow driven salt diapir recycling that we're proposing, and we'll go more in depth in that in the second manuscript. Here we will actually revisit the sediment burial recycling. So on the left column, you see cross sections, and then in the right column, you see map view. What we're going to follow is this key accumulation here through time. So this is 1.5 million years ago. And then this becomes closer to present day through time. And what's happening is because of the dipping sediment, you get sediment burial, and this accumulation migrates upwards and recycles and results in a higher saturation through time. And you can clearly see that in map view as well, with a pretty low saturation of about 5 to 10%, and then resulting in a really high saturation of up to 95%. Now, previously in the literature, what was observed in seismic was at the base of the stability zone, there's this high amplitude reflector that starts to be more dim up dip. And the interpretation was that perhaps the lithology quality actually reduces up dip so that the sandier base has the higher saturations of gas hydrate. Now, we think that that may be possible, or it could be driven by recycling, or perhaps a combination of the two. We saw that the base of this hydrate stability zone aligns well laterally with seismic, and now we're going to look at the gas hydrate saturation and how it aligns with the well data vertically. So it seems to follow a pretty good trend where the model output is here in red, and then the black data points are from the well, and you can see that the lithologies in the light beige here, that's sand, and then in the brown, that's mud. And naturally, we have higher saturations in the sandy layers. And this is the lateral view, or the map view, of the gas hydrate saturation predictions for this model. In the literature, here's a great seismic amplitude map where we see this channel here and then some levees. In the pink, it's predicted to be gas hydrates accumulations, and then the light blue is gas accumulations. What we show here is the gas hydrate saturations, and they seem to align pretty well laterally. So this can help make predictions as far as where they should drill next. We think that the best plan would be to actually drill a well in this area here. And based on discussions at conferences, that is somewhat the plan. They're planning to just step out from a well close to that area, which we think makes sense because other areas are a bit spottier. The final results of this chapter, we make some volumetric predictions. So total methane gas trapped throughout the basin. This includes gas in fine-grained sediment, coarse-grained sediment, and gas hydrate form is about 2 trillion cubic feet. The gas estimate is about 1 trillion cubic feet. And to put that in context, the U.S. Energy Information Administration estimates that in 2018, the U.S. natural gas consumption was about 30 trillion cubic feet. However, much of the methane in this basin may not be economically recoverable due to some low saturations. We really want to target those high saturation accumulations. We made some recommendations. Hopefully these maps can be used to inform the upcoming drilling expedition. And we suggest that this 3D model can be used for future studies which seek to understand gas hydrates as they relate to faults, fractures, lithologic variations, salt tectonics, erosion, pressures, changing water column conditions, temperature changes, and gas sources. Now we'll dive more in depth into this salt diapir associated recycling, which we somewhat alluded to in this previous chapter. I worked with my colleague here, Zach, and we're very excited to show you some of the highlights. So through this approach of basin and petroleum system modeling, we demonstrate that salt diapir movement and associated thermal regime influence to be a mechanism for recycling. Gas hydrate and free gas saturations, plus or minus volumes at the base of the stability zone may be elevated by greater than 10% per million years via this process. We think that this process may explain at least some of the Green Canyon Gulf of Mexico and Blake Ridge US Atlantic gas hydrate saturations, and it implies that salt basins may be attractive for exploration, such as east coast of Brazil, west coast of Africa, and other places in the world. Here is a view of the 2D model created of Green Canyon Gulf of Mexico. On the left column, you see gas hydrate saturations. The right column presents gas saturations. And this panel here includes a salt diapir, and then this panel here has no salt. So you can see some pretty significant differences, particularly that there are much higher saturations, up to about 95% of gas and gas hydrate, when you have the presence of a salt diapir. When you don't have a presence of a salt diapir, now this is the exact same 2D model where we just took out that salt and replaced it with a consistent lithology, we see that the saturations are very low. You have virtually no gas, and the gas hydrates are a saturation of about 5 to 10%. And notice a difference in the base of the gas hydrate stability zone structure. It is flat here, as opposed to domed, which inhibits this focused fluid flow. And notice another thing. There are low saturations throughout the stability zone. And then here, there aren't as many low saturations. It's really just kind of concentrated in one area. We'll take a look at Blake Ridge Atlantic Ocean. So this is the 2D model created where we have the stability zone in red and then not stable in blue. And the difference between the salt model and the no salt model is that this shape here induces more focused fluid flow because it is actually steeper and you have more opportunity for gas capture. Although here it's not flat, here the base of the stability zone follows the seafloor because it's actually closer to the seafloor, which is a strong upper boundary condition. Kind of another way to picture this is looking at the temperature curves. So here's the salt structure, greatly vertically exaggerated. You can see how it affects the temperature in this area where you get this curve here and the higher temperatures at depth, of course. So now we'll go into some different scenarios of these models. This is more so theoretical models. Here we have heat flows or basal heat flows of 35 milliwatts per meter squared in the left, and then higher to the right, up to 65 here. The main observation is what we're calling this kind of sweeping effect. I alluded to this in the Green Canyon model, where there are these low saturations, but they're distributed throughout the stability zone. So what's interesting is that you still have the same volume of gas hydrate in both of these scenarios. It's just that the saturation is pretty different. And if you look at this, you can kind of see this sweeping concept where the base, if it becomes thinner or shallower, there's less room for the gas hydrates to accumulate. Where you have biogenic gas generation, it does not get captured as hydrate. It migrates upwards towards the base. We also tested some different salt diameter scenarios. This was actually brought up at a conference where they were curious, what are kind of the optimal diameters that we want to look for when we're exploring in salt basins for hydrates? We found that 2-kilometer diameter seems to be best. You can't see the salt here, but you can see that it has a really great influence where you have extremely high saturations at the center of the domed base of stability zone. The difference as far as why other diameters are not as optimal is, for example, the 9-kilometer diameter, it just is too broad and doesn't create this focused heat. And then in 1-kilometer diameter, you just have less salt volume, so it has less potential to channel the heat. This was actually something I found quite curious, is the thermal conductivity of sediment. So we wanted to see the relationship between different thermal conductivities of sediment and how that affects the gas hydrate stability zone. So we'll talk about the left column first, where we vary the deep sediment. What I mean by this is the sediment, here's the salt diap here, and the sediment adjacent to it, which we call the deeper sediment, we change the thermal conductivity where it's low here, and then greater and greater here to about 2.4. And what's happening with the stability zone is it's thinning when you get a higher thermal conductivity. So the reason that that's happening is because this deeper sediment, when it has a higher thermal conductivity, it's more effective at conducting the basal heat flow upwards and thinning the stability zone. But the opposite happens when we change the thermal conductivity of shallow sediment. So here you can see the low thermal conductivity of shallow sediment, so everything above the salt diap here, and then it's higher here. And the opposite effect occurs where with the higher thermal conductivity, there's a thicker gas hydrate stability zone. And this is because now, conversely, the sediment's more effective at conducting the upper boundary condition of a cool seafloor temperature, which thickens the stability zone. So this is pretty important to keep in mind when you're creating these basin models. Another thing we wanted to think about was salt movement and how different scenarios affect gas hydrate saturations. Here's a sketch that I created in which you have two scenarios. In this upper part, the salt diap here is actually evacuating through time. And what happens is the base of the stability zone shifts downwards. And then where you had a high saturation accumulation, it's now found in the middle of the stability zone. So we think that whenever you have thickening of a gas hydrate stability zone, that's when you're most likely to find gas hydrate accumulations throughout the stability zone rather than just at the base. And then when you have salt growth, you have this kind of sweeping effect where the stability zone thins and it results in higher saturations. Overall, some of the main takeaways from this manuscript are that the impact of salt via its impact on heat flow, on gas hydrate system dynamics, it's relatively unexplored in the literature and consists of this proposition that it's really an inhibitor of gas hydrate formation, or of heat flow as a catalyst for destabilizing gas hydrates, whereas the potential for salt-related heat flow to have the opposite effect and enhance hydrate saturations hasn't been invoked, and we think that this is something that we should be considering. Hopefully these scenarios can help with exploring the different types of salt structures we want to be looking for. And this recycling may be contributing to what we see at these case study sites that we also coupled with the synthetic theoretical models. Another thing that we thought would be important is to maybe consider including salt bathymetry maps in these maps that have been, there's a few maps that have been published which predict gas hydrate stability zone thicknesses globally and also in different basins. And we think that if you incorporate a bathymetry map of the salt in these map predictions, it can help actually show this variation of gas hydrate saturations and maybe refine the maps a little bit better. Now we dive into actually my favorite manuscript. This is the global sensitivity analysis coupled with BPSM, or Basin and Petroleum System modeling. It's a novel and automated approach to unraveling gas hydrate and gas complexities. I collaborated with Marcela Brasil-Silca, who is a PhD student at Stanford as well in geological sciences. We'll briefly cover the method that was used. We created an in-house code for automation using Python and MATLAB, and we applied Monte Carlo. This is based from a former student, Mustafa Al-Ibrahim's toolbox, and this code can be used for conventional studies as well. Marcelo was the primary help in developing this custom code by translating my human language and design to kind of computer language. Here are some of the outputs. So we created thousands of unique 2D basin and petroleum system models for gas hydrates. And to put that in perspective, there have been about 34 of those published so far in the literature. We also have organized spreadsheets of tens of thousands of values, including inputs and outputs extracted from all the models, which we think can be used as a helpful database. Now, I mentioned sensitivity analysis. Overall, it is how the variation of uncertain input parameters for models, for example, impact the uncertainty of the response or the output. It ranks data acquisition importance, and it identifies unimportant inputs to simplify complex problems. There's two main types of sensitivity analysis, including local and global. The local sensitivity analysis approach utilizes a small percentage of the design space, especially when there are many inputs. It's a simple screening method widely used across disciplines, and it's the only sensitivity analysis method used so far for understanding gas hydrates in basin and petroleum system modeling. There's been about 8 such studies. It is a qualitative and subjective measure of sensitivity, and it does not evaluate parameter interactions for nonlinear effects. Here's an example of a local sensitivity analysis output where you have a tornado plot comparing different input variables and a base case output here and how it increases and decreases, this variable 1 being the most sensitive. In global sensitivity analysis, which we also use in this manuscript or project, is that it's quantitative and it's an objective measure of sensitivity. And it evaluates parameter interactions for nonlinear effects. What I show here is a heat map, and in the diagonal, you can see the sensitivities of the actual inputs plotted against themselves. So this input here is considered the most sensitive or critical. And then here, these are insensitive and not really important for the function of the system. Where you're outside of the diagonal, here you have interaction effects. So how the different variables or inputs interact with each other, whether they're sensitive or insensitive. Here are the initial histograms. Overall, these are for the known sites. So what I did is I took statistics or data from the 50 different gas hydrate sites globally, which have been drilled and inferred, to basically be as an input for the Monte Carlo to select randomly throughout these distributions to create different realizations or different model scenarios. I'd like to point out that for the organic properties, which is important for the generation of gas, when you have higher organic properties, more gas is generated. We took these distributions from Burton and Hertfordshire, which is in preparation now. One thing that we changed, so we will be presenting two main types of models, so two different sets of models. One, like I mentioned, is the statistics from these known sites, and then one is actually from global sites. So we take actually the global distributions, such as water depth. And you can see a big difference here. The known sites have been drilled at shallower water depths, but globally, we have a lot more abyssal plain, where the water depths are more so around 4 kilometers deep. We varied some other inputs as well to really represent global basins in this case. And these are essentially 9 different inputs that we vary. We have variations in initial porosity of sediments and other sediment properties, including boundary conditions of the models. I should mention that the lithology we used is a mixed mudstone, and this is because we can incorporate different types of mixed mudstone lithologies, such as some that contain more carbonates, some that contain more sand, and it gives us a bigger range of initial porosities and thermal conductivities and the like. Here's an example of one of the 2D models that was realized by the Monte Carlo. It's about 6 kilometers across. There are 33 layers at depth. It is 1,800 meters thick, each layer being about 50 meters thick. We have 30 grid lines across, so you can see each of these in an individual cell. And we have a dome here at the base, which shallows upwards. We found that when we had flat sediment layers, the gas hydrate accumulations were far too random. We didn't have any focused fluid flow. And it's not really representative of nature. We want some sort of relief, some sort of geologic variation. So here we have a relief of up to 150 meters and a dip of up to 10 degrees. First, we'll look at the gas hydrate stability zone output analysis. So we'll be looking at 3 different outputs, and we'll start with the gas hydrate stability zone thickness. And we will look at both the local sensitivity analysis results, and then in the next slide, we will see the global sensitivity analysis results. This is kind of the first screening method, the one that's most commonly used in studies. In the global scenarios, so this tornado plot is actually the global distributions that were used. And then here we have the distributions for known sites. The base case is about 500 meter thickness for the global scenario and about 200 meters thickness for the known sites, which makes sense because you have greater water depths here, therefore greater pressure and a thicker stability zone. What we see in red is that the basal heat flow seems to be the most sensitive input parameter. What we mean by that is it's potentially the most important for determining the output. And perhaps the water depth is the second most important. Now, whether these other input parameters are impactful is somewhat subjective here. Different interpreters would likely provide different conclusions. And then this is the global sensitivity analysis results for the gas hydrate stability zone thickness, with the global distributions here and then the known sites here. We can see that, on the other hand, more inputs are important for the system than what we saw previously. We still have basal heat flow and water depth as important input parameters, but we also have seafloor temperature, initial sediment porosity, and thermal conductivity. We can also see parameter interactions here, and these can be used when you're constructing basin and petroleum system models. And what I mean by that is, we'll take this example where basal heat flow interacts with thermal conductivity of sediment. What this means is that when you vary the thermal conductivity or the basal heat flow, they have a relationship. So you have to consider or confine both of them. On the other hand, if you look at TOC or organic properties, compared to the basal heat flow or plotted against it, it's not sensitive. So what this means is that the basal heat flow will result in a certain output no matter what the total organic carbon input is. For the known sites, overall there's similar input parameters which are important, but at different amplitudes. You can see some variation here compared to this heat map. And thermal conductivity is not an important interaction. Water depth and seafloor temperature seem to be even more important for these sites, whereas basal heat flow is less impactful. And this is somewhat intuitive because at these greater water depths, the base of the stability zone is closer to the seafloor, which has more of an effect than the basal heat flow. Now for the second of the three outputs, which is the gas hydrate saturations or accumulations. We'll look first at the local sensitivity analysis results, which are these tornado charts here. Globally, the base case model has a maximum gas hydrate saturation of about 19%. So that's what we're looking at. We're really looking at the maximum saturation that exists in the model. And the sensitivities for the gas hydrate saturations are different than those for the gas hydrate stability zone thickness. But we may see that that's different in the global sensitivity analysis results. It seems that the minimum water depth may be the most important input parameter, but it's somewhat inconclusive because the gas hydrate stability zone simply does not exist at this thin water depth, which is at 300 meters, which is where gas hydrates have been found at the shallowest in the world. We would need to actually change the basal heat flow as well in order to keep some sort of gas hydrate stability zone thickness to look at the saturation and how it would be sensitive. Would it be higher with this lower water depth or lower? But here we can only vary one parameter at a time. For the known sites, the base case scenario has up to 55% saturation, so keep that in mind. In the known sites, we seem to have more promising accumulations. Now, this tornado plot is somewhat strange. Essentially, every variation reduces the saturation of the models compared to the base case. Now, the reason we think that is because the base case is somewhat of a Goldilocks scenario where you have a very high saturation, and when you perturb the system, it results in lower saturations. But relative to each other, the input parameter relationships make sense. So for example, when you have a low total organic carbon, you have a lower saturation compared to the base case model. But when you have a higher TOC value, you still have a lower saturation than the base case, but it's not quite as low. And this makes sense relatively speaking. Now, what's great about the global sensitivity analysis is instead of using this limited amount of tens of models, we actually have thousands of models. So more model scenarios can be compared to the base case, and we can observe these sensitivities beyond this pretty strange tornado plot. Here are the results for the saturations. We'll first talk about the global ones, where it's actually similar to the gas hydrate stability zone sensitivities, with addition to organic properties. So this implies somewhat of a relationship between hydrate stability zone thickness and resulting saturations, but organic properties are important here, which makes sense because they control how much gas is generated in the system. 88% of gas hydrate accumulations, which have greater than 30% saturation, have stability zones that are less than 543 meters thick, and they have shallow to mid-water depths. We think that there's an importance here to think about. Basically, when you have shallower water depths and thinner stability zones, these higher saturation accumulations occur due to two reasons. You have less space. So a thinner stability zone means that some of that deeper biogenic gas that's being generated can migrate up to the base and accumulate at higher saturations. And then we have to think about gas phase. At greater water depths, the gas phase tends to be liquid, and then in shallower water depths, the gas phase is in vapor form. And vapor migrates more effectively than the liquid phase and results in higher saturations. The interpretations for the known sites are that overall there are more optimal geologic conditions, so the organic properties are less sensitive or important for the system here. 97% of the promising accumulations, so about 740 models, have relatively thin stability zones, so this kind of goes along with that theme. And 100% of the models with geobodies or promising accumulations have shallow to mid-water depths. This is the last output we'll be looking at, which is gas saturations. Gas saturations, which exist beneath the gas hydrate accumulations. You can see the two tornado plots for the local sensitivity analysis here. And I'd like to point out that for the known sites, it's still that type of tornado plot where most cases reduce the saturation percentage, but some of them increase it. So we do think that these the analysis was actually performed correctly. The gas saturations are similar to the gas hydrate saturation sensitivities. And again, the minimum water depth used eliminates the stability zone, so all the gas escapes from the seafloor, so we cannot really understand whether it's important or how it's sensitive. In the known sites, as I mentioned, we have somewhat similar tornado plot, and we like to see that there's actually greater saturations in some of the scenarios. Again, for gas saturations, here are the global sensitivity analysis results. Some quick observations include that globally, the output parameters solely depend on the inputs of water depth and basal heat flow. So overall, this means it's a much simpler function. For the known sites, they're similar to the global impacts, except that seafloor is also important. And I mentioned why before, and it's because it's closer to that upper boundary condition. We then wanted to look at correlations in the database where we have those tens of thousands of inputs and outputs. Now, the reason the global sensitivity analysis was helpful is because it figures out these correlations in different dimensions, because when you have this complex analysis, you can't just plot two different outputs and inputs and find correlations very often. But we did for the gas hydrate stability zone thickness and the basal heat flow. Here you can see the global results. So these blue points are the gas hydrate stability zone thickness for each of the models, about 600 models here and 1,500 models here, plotted against basal heat flow. Why does this correlation matter? Basically, what we propose is that this can be used for conventional energy exploration. This is because it is important to constrain the basal heat flow to study a basin for conventional hydrocarbons, because this can determine the difference between oil or gas generation. And typically in basin petroleum system modeling, what I found discussing this with experts in my own experience is that basal heat flow tends to be one of the greatest unknowns when we're building these models and studying these basins. So how is this applied to conventional study? Let me explain it further. Basically, if you have seismic, 2D or 3D seismic in a new venture's relatively unexplored basin, you can typically see a BSR where a gas hydrate stability zone or gas hydrate accumulations exist. So what you can then do, say you take a 600 meters thick gas hydrate stability zone that you observe in seismic, you can work backwards, use this correlation, and see that the basal heat flow for this basin is likely between 30 and 50 milliwatts per meter squared. And this actually aligns with the case study that we performed in my first project. So here you can see when you have a gas hydrate stability zone thickness of about 1 kilometer, the likely basal heat flow is around 25 milliwatts per meter squared. So we're very happy to see that this correlation aligned with one of our case studies. Now we'll wrap up quickly here with the novelties and conclusions of this project. Thousands of these 2D basin and petroleum system models were randomly built using Monte Carlo. From start to finish of this process, which includes everything from the Monte Carlo to the simulation, to the analysis of the sensitivities, increased the time efficiency by about 40 times compared to the traditionally used method, and it eliminates sampling bias. This is the first application to gas hydrate BPSM, and it's useful for conventional oil and gas studies as well. Two input parameters for gas hydrate stability zone thicknesses were important. And looking at our local sensitivity analysis interpretation, that's not the same as what we thought in the global sensitivity analysis, where it seems that 5 are important. Local sensitivity analysis seems to be inconclusive for gas hydrate saturation, while global sensitivity analysis shows that gas hydrate saturation sensitivities are similar to gas hydrate stability zone sensitivities, but organic properties are also more important for global basin scenarios. So they should be added to gas hydrate saturation global map predictions, particularly for deep water. Saturation is overall a simpler function than gas hydrate saturation. These promising accumulations are more likely to occur in shallow to mid-water environments than deep water basins, which is really great to see because it's cheaper to drill. Sedimentation rate and average ocean water salinity were consistently unimportant to the system. Now, I would like to briefly say that the reason we considered sedimentation rate is because it actually affects the temperature of the basin, where when you have higher sedimentation rates, you have a blanketing effect, where the basal heat flow doesn't have as much time to heat up the sediment, so it results in a thicker stability zone. And then ocean water salinity we looked at because salinity actually inhibits gas hydrate saturation. We have thousands of models which can contribute to understanding of gas hydrates. Previously, there have been about 34 that exist, and we hope that our spreadsheets can also inform basins with missing information. The global sensitivity analysis heat maps can be used as guides for which interactions should be paid attention to. And these correlations between basal heat flow and gas hydrate stability zone can be used for conventional exploration. Broadly, what we covered here is a case study in the Gulf of Mexico to inform an upcoming drilling expedition, proposal of a mechanism occurring in salt basins for attractive exploration, a novel method approach for a global understanding of gas hydrates. And I'd like to say that actually a future recommendation to students or industry and alike is to conduct this dissertation study in reverse order, because we actually would like to do a sensitivity analysis first to determine which inputs are most important for us to pay attention to as far as data collection and narrowing the uncertainty before we really dive into a complex case study.